at how does delta G free energy relate to equilibrium constant K. So by this equation, so delta G is equal to delta G on standard state plus RT ln the Q. And if you remember what Q is from previous chapters, Q is a reaction quotient, which is basically just the calculation of K to see if you're at equilibrium or if you're not at equilibrium. Okay, so at equilibrium, then Q is equal to K, and at equilibrium delta G is equal to 0. So if we plug those into this equation above, so 0 then equals delta G naught plus RT ln of K. So if we plug K in for Q and delta G equals 0 in, then we can rearrange this equation. So delta G naught equals negative RT ln of K. So then if no delta G naught, which we just looked at several examples where you can calculate it using thermodynamic data, then can calculate K. Or vice versa, if you know K, equilibrium constant, based on what we've covered in previous chapters, then you can calculate delta G thermodynamic data from that. So if we take an example, so what is K for the reaction below at 25 degrees Celsius? So if we use delta G 0 values to determine K, so for this reaction, so if we go to appendix C and look up delta G formation values for these different compounds. Okay, so for calcium carbonate, it's negative 1028.8, and these are all kilojoule per mole values. For calcium oxides, negative 603.5, and for CO2 gas, negative 394.4. So delta G0 would equal products minus reactants. So negative 603.5 plus negative 394.4. And then subtract off your reactant, negative 1028.8. So delta G is equal to positive 130.9 kilojoules. So first of all, if you recognize, so delta G is positive, so that means this reaction is not going to be spontaneous, and it's much larger than 10 kilojoules per mole, so K should be extremely small. Okay, so now we can solve for K using this equation, delta G naught equals negative RT ln of K. So if we want to solve this for K, so delta G naught divided by RT equals ln of K. So ln of K is negative delta G naught divided by RT. And if you remember the mathematical manipulation, if you want to get rid of ln, then what do? So e to the ln of K equals K, right? So then K equals e to the negative delta G over RT. So I'll just plug in values and solve. So K equals e to the negative 130.9 kilojoules divided by R. So R is a constant. It's 8.31 joules per mole Kelvin. And at 298 Kelvin, so you got to convert the 25 degrees Celsius that was given. Convert that to Kelvin. And the constants in joules, but delta G that you calculated is in kilojoules, so we need to convert joules to kilojoules. So 1 kilojoule is 1,000 joules. Okay, so if we calculate that out, K then is equal to e to the negative 52.86, which is 1.1 times 10 to the minus 23. So very small number. So this reaction would not be product favored, it would be heavily reactant favored. So if we take another example, so 18.9 from the textbook. So any K, any equilibrium constant, like we talked about from early in the semester, or equilibrium constants from acid-base reactions, or equilibrium constant KSPs from solubility products. Doesn't matter which one, the equation works for all of those. So calculate KSP for the solubility of magnesium hydroxide in water at 25 degrees Celsius, and use thermodynamic values for delta G0 formation in order to do this calculation. So delta G0 formation values. So if you remember, KSP is, well, so we ignore the water, right? So we're going to ignore the water. Okay, so negative 833.7 kilojoules per mole for magnesium hydroxide. For magnesium aqueous, it's negative 454.8, and hydroxide, negative 157.3. So we have to multiply the hydroxide times 2, since there's 2 of them. Okay, so delta G is equal to 64.3 kilojoules. So again, it's positive, so this is, and it's large, greater than 10 kilojoules, so this is, K is going to be a very small number again. So magnesium hydroxide is not very water soluble. Okay, so K then is equal to e to the negative delta G over RT. So just plug in and solve. So negative 64.3 kilojoules over 8.31 joules per mole Kelvin. And we said 25 degrees Celsius, so 298 Kelvin. And again, convert kilojoules to, or joules to kilojoules. Okay, so K is 5.29 times 10 to the minus 12. Okay, so then again, one thing that's always interesting for a chemist to know is at what temperature, or so would a reaction be spontaneous, and if it's temperature dependent, then at what temperature would that reaction become spontaneous? And so in order to figure that out, so again, we just use this equation, delta G equals delta H minus T delta S. So at equilibrium, then delta G equals 0, so 0 equals delta H minus T delta S. So if this term equals 0 at a certain temperature, so let's solve for temperature. So T delta S equals delta H. So T is equal to delta S over delta H. So at a certain temperature, then delta H minus T delta S is 0. If you go 1 degree above that temperature, then delta G would now become negative, and that reaction would be spontaneous. So we're going to figure out what the temperature is, and then any temperature above that temperature, delta G would be negative, and this reaction and the reaction process would be spontaneous. So if we take an example, so for calcium carbonate to become calcium oxide and CO2, so delta H is 178.3 kilojoules, delta S is 0.1590 kilojoules per Kelvin. So just take delta S, sorry, didn't do that right. It's delta H over delta S. Okay, so we just plug in our values, 178.3 kilojoules over 0.1590 kilojoules per Kelvin. So at 1121 Kelvin, you're at equilibrium. So any temperature above that, so that's 848 degrees Celsius. So any temperature above 1121 Kelvin, or the reaction would become spontaneous at that point because delta G would become negative. And if we took one more example, so sodium bicarbonate decomposes into sodium carbonate, water, and CO2. At what temperature would this reaction become spontaneous? So if you're not given any delta H or delta S, then you have to calculate it yourself. So use appendix C and look up these values. So negative 950.8, negative 130.8, negative 241.8, and CO2 negative 393.5. These are all kilojoules per mole. And for delta S, 101.7, 138.8, 188.7, and 213.7. And these are all joules per mole Kelvin. So again, either those numbers would be given to you, or you would have to look them up in a table. So now we can calculate delta H and delta S. So take your products minus your reactants. So again, because of the 2, you got to multiply this number by 2. So delta H 130 is 135.5 kilojoules, and delta S is 337.8 joules per Kelvin. So temperature then equals delta H over delta S. So 135.5 kilojoules, and then over the 0.3378 kilojoules per Kelvin. So we need to convert to kilojoules. So at 401 Kelvin, you're at equilibrium. And so then at any temperature above 401 Kelvin, delta G would be less than 0, would be negative. So spontaneous. Okay.